Check it out, guys. University of Arkansas News, Saturday, October 3rd. That'd be today. Physicists build circuit that generates clean, limitless power from graphene. Really? Let's just check it out. Oh. Mm-hmm. So no sound on that, I guess? Wow. A simple energy harvesting chip under development. A sample energy harvesting chip undergo testing. Uh-huh. Wow. So out of Fayetteville, a team of University of Arkansas physicists has successfully developed a circuit capable of capturing graphene's thermal motion and converting it into an electrical current. An energy harvesting circuit based on graphene could be incorporated into a chip to provide clean, limitless, low voltage power for small devices or sensors, said Paul Thibodeau, professor of physics and lead researcher in the discovery. The finding, titled Fluctuation Induced Current from Freestanding Graphene and published in the Journal of Physics Review E, are proof of a theory that physicists developed at the U of A 3 years ago that freestanding graphene, a single layer of carbon atoms, ripples and buckles in a way that holds promise for energy harvesting. The idea of harvesting energy from graphene is controversial because it refutes physicist Richard Feynman's well-known assertion that the thermal motion of atoms, known as Brownian motion, cannot do work. Thibault's team found that at room temperature, the thermal motion of graphene does, in fact, induce an alternating current in a circuit, an achievement thought to be impossible. In the 1950s, physicist Leon Brillouin published a landmark paper refuting the idea that adding a single diode, a one-way electrical gate, to a circuit is a solution to harvesting energy from Brownian motion. Knowing this, Thibaud's group built their circuit with two diodes for converting AC into DC. With the diodes in opposition allowing the current to flow both ways, they provide separate paths through the circuit, producing a pulsing DC current that performs work on a load resistor. Additionally, they discovered that their design increased the amount of power delivered. We also found that the on-off switch-like behavior of the diode actually amplifies the power delivered rather than reducing it, as previously thought, said Thibodeau. The rate of change in resistance provided by the diodes adds an extra factor to the power. The team used a relatively new field of physics to prove the diodes increased the circuit's power. Improving this power enhancement, we drew from the emergent field of stochastic thermodynamics and extended the nearly century-old celebrated theory of Nyquist, said co-author Pradeep Kumar, associated professor of physics and co-author. Y'all are going to start seeing this kind of technology emerging more and more. According to Kumar, the graphene and circuit share a symbolic relationship. Though the thermal environment is performing work on the load resistor, the graphene and circuit are at the same temperature and heat does not flow between the two. That's an important distinction, said Thibodeau, because a temperature difference between the graphene and circuit in a circuit producing power would contradict the second law of thermodynamics. This means that the second law of thermodynamics is not violated, nor is there any need to argue that Maxwell's demon is separating hot and cold electrons, Thibodeau said. The team also discovered that the relatively slow motion of graphene induces current in the circuit at low frequencies, which is important from a technological perspective because electrons function more efficiently at lower frequencies. People may think that current flowing in a resistor causes it to heat up, but the Brownian current does not. In fact, if no current was flowing, the resistor would cool down, Thabato explained. What we did was reroute the current in the circuit and transform it into something useful. The team's next objective is to determine if the DC current can be stored in a capacitor for later use. Of course it can. A goal that requires miniaturizing the circuit and patterning it on a silicon wafer or chip. If millions of these tiny circuits could be built on a 1 millimeter by 1 millimeter chip, they could serve as a low-power battery replacement. The University of Arkansas holds several patents pending in the U.S. and international markets on the technology and has licensed it for commercial applications through the university's Technological Ventures division. Researchers, blah, 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 contributed to the work, which was funded by the Chancellor's Commercialization Fund, supported by the Walton Family Charitable Support Foundation. Yeah.